Can you hear me? Hello? Hello?
Yes.
Yes.
Yes, sir. Yes, sir.
Screen is visible?
Yes, sir.
Okay. Well, last time I talked nonlinear space. That I told you that nonlinear space actually we have this x with a norm like a metric, but x is a linear space, vector space over f, where f equal to R or C. In this course, I'm taking basically R. So, and non-function, I told you it behaves like this on R. Okay, so then this together like a metric space is called a non-linear space or non-vector space. And I told you that this gives you a metric actually. This gives you a metric Txy equal to this. And I said particularly the example I was giving that if you take, don't confuse with that x now. X is a non-empty set and Px, the linear space, vector space of all real valued bounded functions on x. Then for each f belongs to Px, define this. This is a special notation for this particular norm. Soup of check that this is a norm. When you check the norm, basically you'll have to use this thing, mod function on R. Check this dot, meaning is that there has to be a vector has to be put there. Usually we put right like this. That means there is a blank. You'll have to fill up the vector here. Is a norm on Px. And this norm has got different name. This is called soup norm. Because of this infinity norm, because of the notation, or called uniform norm because this gives you exactly topology of uniform convergence, uniform norm. Okay, so this is very important in both in analysis and function analysis. Okay, so that this is norm on Bx. Now suppose I'm explaining that X is a topological space. Now suppose some topology you can take. Okay, then Cx is the space of all real valued continuous functions on X. Now look, a function may not be bounded here, but still, as you know, that again I will define, last semester I did, I can define still uniform convergence of sequence of functions. That I'll tell you that with respect to which metric we can do. But here it is need not be bounded function unless X is compact. Unless X is compact. Okay. Unless X is compact. So that basically you'll have to look at this CBX, which means F belongs to CX, F is bounded, that means Fx is bounded in R. That means we're taking real valued bounded continuous function, which means we're taking actually this. So in particular, this is a subset of this, actually linear subspace of this. This is also linear space, so that this is a linear subspace. Of Bx. So in YAL you can, here you can give this norm CBX, this infinity norm. This is a non-linear space. Okay. But what about Cx? So the Cx, okay, Cx, what you can give a metric that will play the role for uniform convergence. Cx, look, I may not be able to give a norm, but I will be able to give a norm which will metric which will give you the uniform convergence. First, let me recall that. Suppose this r to the power x. Remember that r to the power x means it is all collection of functions from x to r. Okay. So if you have a sequence of functions in this thing. Here I am not talking about any topology, but I can give a metric that exactly I want to do it. I want to do it here, then it will come here when X has a topology. So now Fn in Rx and F belongs to Rx, then now look, if for each X, definition recall, for each X belongs to X, Fn X is a sequence in the real line. So Fn X converges, I'm not saying you will have it, converges to Fx in R. Suppose for each X, suppose for each X you have this, actually it's a sequence of real numbers, then we say that Fn converges to F pointwise convergence. Okay, so pointwise convergence actually is shifting the convergence to the real line. You could have complex, if you had a complex valued functions, then you'd have complex plane. But what about uniform convergence? Now look here, when I say pointwise convergence, it means what? Fn F belongs to this, and Fn, I'm recalling what I taught you last semester. I'm again teaching you that pointwise. It means given X and given epsilon, and given epsilon greater than 0, there exists n depending on both such that in set of naturals such that Fn X This is to show that, to make sure that here you have two bars, with one bar. This is a natural number. So that if you have this, if it happens for each x, suppose we have it given x, that means for each x, then it is called pointwise convergence. But this n is depending on epsilon as well as x. Suppose it is possible. Suppose this n only depends on epsilon, not on x. That means what will I will get? That means suppose you have it given epsilon greater than 0, there exists n epsilon only depending on epsilon, such that fn x this less than epsilon for all n greater than equal to n epsilon, and for all x belongs to x. Suppose you have it, then we say that fn converges to f uniformly. Fn converges to f uniformly. So this uniform convergence is stronger than pointwise convergence. Okay. That last semester I gave you that example that a pointwise convergent function need not be uniformly convergent, x to the power n on the closed interval 0, 1. So this is uniform convergence. Now look here, this means you have this. This is less than equal to epsilon. I am taking so. Okay, that means look, this is less than equal to epsilon, so this is a real number. So the thing is that means fn is less than equal to epsilon coming for all n greater than equal to n epsilon. But the problem is that, so it is fine. So here it gives an idea that, but now suppose in NAL I may not know unless it is bounded function. That means soup of this. Here if fn converges to f uniformly, then I can always have this. But otherwise in NAL, suppose between two functions, this may not be a real number. Yeah, that means it may be infinity. But there is a thing that how I may not get a norm, but I can get a metric D, okay, such that it will give me the same convergence. How to do that? Okay, this may be infinity, but if I define this, look what I'm doing it. Okay, soup of fx minus gx hey, who is making awaj? Huh? Look, soup may not be an R, but each of them is an R because they are real valued function. Each of them is an R. So this is a real number. So this is a real number. This value will be always less than or equal to 1. Look, this is well defined. That's why we are taking 1 plus. Even it is 0 in the denominator, I will have 1. And it can't be 0 because this is a non-negative number. It will be always greater than or equal to 1. Denominator. Always greater than or equal to 1. And this is less than or equal to 1. So here you get a metric. And this is actually in the metric, if you look in the ball, when you think of that, the metric, this R, actually you need to take all the time for your purpose of proving results on that to small, not to the large. Okay. And so that you can always take them to be less than 1. So that is exactly happening. Here D metric itself, I could check that D is a metric. Check D is a metric on r to the power x. Okay, right? And of course, D is less than equal to 1. Okay, now you can check that here. I'm giving you this exercise. You should do that. In the Alipranthis Barkinsaw, you see that exactly what I'm saying. Alipranthis Barkinsaw, page 78, number 11. Problem number. Okay. Now, exactly the first thing that part A is saying that 11A. This is exactly that. Check T is a metric on R to the power x. And next thing is that in part B is saying show that a sequence Fn in R to the power x satisfies to 0 for some, of course, real ordered function. It belongs to Rx if and only if Fn converges uniformly to F. Okay, so that uniform convergence we can tackle in terms of the metric also. Okay, and when you take a collection of bounded functions, so look, Bx is R to the power x, then Bx you have the metric given by this and also this metric D. Of course, you can check their equivalent metrics. So the topology will certain topology will be same. So you have this is called the topology of uniform convergence. The topology given by D or this whatever is called the topology of uniform convergence. Topology of uniform convergence. In fact, a sequence on net, if you are talking about convergence, that always has to be with respect to some topology. So here, first you define uniform convergence without any topology, but then I say that then I prove basically in this result, in this problem, that actually convergence with respect to some topology, which is called the topology of uniform convergence. Okay. When you have this like Bx, it will become a nonlinear space, but Rx to D, you can check that this is not a nonlinear space because this is not a norm. This is not a norm. That you should check why it is not a norm. Okay, right. And so make sure that you do that. This is any uniform convergence. I mean, for pointwise convergence also that is a topology is there. That if I give time, I'll just explain one day. That topology of pointwise. When I say pointwise convergence, that is also on R to the power h or cx, I can give a topology, which is called topology of pointwise convergence. Okay, so that here I could give another metric. Look, what is this metric I could give? That G prime Fg, the minimum of, that is I could bound by 1 sup of minimum. Look, so if this becomes infinity or greater than 1, basically, particularly infinity, then it will come 1. Otherwise, and if it is less than equal to 1, then I will have this. And you can check that also that D prime is equivalent to actually many authors take this metric for topology of uniform convergence. Okay, right. Now, the first thing that I proved last time, I said that it is 3 epsilon argument, theorem 9.2. You should not forget. Okay. Look here, of course, you have a topological space, page 69. Again, you should look. Extra is a topological space, so you can consider continuous function. And suppose you have a continuous functions. Now look, here Fn actually is taking topological function, is taking this sequence of continuous functions converges uniformly. So suppose it is in Cx. It makes sense because I have taken a topological space. And suppose Fn goes to F uniformly. Here actually means uniformly in R to the power x. Okay, these are hypotheses. If you have a topological space, you have a sequence in functions here, and this is this, and then he's saying f will be also continuous. That is, the uniformly convergent limit of a sequence of continuous functions is continuous. Implies f belongs to Cx. Now look, with this metric or this metric, R to the power x is a metric space, and I am getting this. That means what actually means? Cx is a, this is a complete metric space. Because if you take, well, this is a complete metric space. Why? Now you should check that Rx to D, that D I have given, that Alipanthis Barkinsa question number 11. Yeah, that problem. You should check also, they have, D is a complete metric. Okay, you should check that. It is a complete metric actually. Okay, so that if you can do that, then Cx will be a subset of this, the uniform convergence, that is Cx D. Here functions may not be bounded. That's why I am taking D. So what this result particularly says, uniformly convergent. Look, here is theorem 9.2. Actually, informally say that a uniformly convergent limit of a sequence of real valued continuous functions. Of course, X has a topology of real valued continuous functions on X tau. Uniformly convergent limit of a sequence of real valued continuous functions is again is also continuous. On this. This is the actual statement of theorem 9.2. But now look, if I take a Cauchy sequence here, then because if you have this, then it will converge there. And that means then I'll have the uniformly convergent limit of that sequence of functions. So that will be by this, it will be there. So there's actually says this result is a complete metric space. But in order to prove this, you need this result as well as this thing. This I'm leaving as an exercise to you. Okay. That what 11 is also I'm putting C, that so that this is a complete metric space in that. Okay, the way you proved, remember that Vx with that exactly gave the supremum metric. Same way you proved that, try to construct a function, real valued function, to which it will converge uniformly. Technique will be the same. You should check that. And Also, you be using the completeness of R. Completeness of R. So this is theorem 9.2, and again you should remember this is known as so-called standard 3 epsilon argument, because we will split into 3 parts. Okay. Now that exactly soup norm he gave that I talked last time. Okay. Look here, theorem 9.3. Look here. Actually, look, theorem 9.3, I can write this. I don't need compactness, I'm telling you first. What I can do, let X tau be a topological space. Then CBX with this norm is a Banach space. Here is he saying complete. Actually, his compactness is required for different thing. But let me tell you. So theorem 9.3 is this. Banach space, you remember, this is means complete nonlinear space. But the completeness comes because of the metric. So that exactly he is saying. But I do not need compact. If X is compact, that by a previous result it will mean Cx equal to Cbx. That is coming. But otherwise in the proof, we can look at the proof. We are proving this, not you don't, otherwise you don't require compactness. So it's a complete nonlinear space. But in particular, it's a complete metric space. Look, how will you prove that? Take a Cauchy sequence here. Suppose Cauchy. But this is a subset of Bx. So this implies Fn is Cauchy in Bx. Metric given by this. But this is a complete metric space. So that there exists a function Fn B. Okay, converges uniformly, where AF is belongs to Bx, because Bx is complete and Fn was a Cauchy sequence there, so it belongs to Bx. But each Fn is continuous, and since it is uniformly convergent by theorem 9.2, F is also continuous. That exactly needed to prove that F belongs to Cbx. F belongs to Bx, F is continuous, so F belongs to Cbx. So actually, result is proved that Cbx theorem 9.3 actually says just assume X tau is a topological space, need not be compact. Cbx is this. That is a Banach space. समझ गया? So this is theorem 9.3. Okay, fine. Now I want to prove Dini's theorem, the theorem 9.4 that I proved last meeting, but again I'm talking about the theorem 9.4. Dini's theorem. Look here, the question is that when pointwise convergence of a sequence of functions will imply uniform convergence. So Dini's theorem is in that direction. But Dini's theorem is saying, look, let's explain Dini's theorem first. Okay, right, that he's saying X tau is a compact space. So be careful about that compact. Right now I'm taking compact. Okay. And he's saying, suppose you have a function, monotone function. Monotone function means it can be both ways. That means it is increasing or decreasing. What is the meaning of that? Last time I said, when I talking about lattice, with respect to that order, I said two functions there. If fx less than equal to gx for all x. This was a partial order. This is the order I gave. Same way here, the same order I am taking. Here fn is increasing, matlab that fnx less than equal to fn plus 1x for all x belongs to x. Then fn is called increasing. It's called increasing. And often we use this notation, the arrow. It means it is increasing. Okay. And opposite thing will be decreasing. That means if you take this, for all x, for all n. This if suppose you have for all x and for all n. Then fn is called decreasing. If it is either increasing or decreasing, then it is called monotone. Like the monotone sequence in R. Here I am taking sequences in functions, sequence of functions, but still I can have that idea monotone. Okay, it is either increasing or decreasing. Actually, while dealing with this any result, I need to deal with either increasing or decreasing, like real numbers. Because if fn is increasing, if and only if, here you use the notation decreasing. If and only if minus fn is decreasing. Okay, so while proving, you need to only prove one thing. So here he is saying Dini's theorem. That you have this, the monotone sequence that I already explained, converges pointwise to a continuous functions. Here you have this topological space, so you have the continuity you can have Cx. And suppose Fn, each Fn, this is a subset of Cx such that Fn converges to F pointwise. 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 Okay, in Cx. Here he's assumed that this is compact. Okay. Then it implies Fn actually converges to F uniformly. Look, it's a very special case. Look, I am taking compact here, I am taking monotone function. He proved for increasing, decreasing, you can have the same proof, or you can go for minus Fn. Okay, right? So that this is the thing, the pointwise converging, but he is taking compact, he's taking monotone, and then if this thing, it is not only pointwise sequence of functions and that limit will converge uniformly. It is not. He's having two hypotheses, compact and particular class of function. Now look how he proved actually. Let me tell you that how he proved that. He assumed that you must read the proof carefully. Okay. Now look, suppose you have this increasing, it means that pointwise convergence, that it is increasing. Okay, it is converging to F, but and this function is increasing. Okay, now he is proving that take any epsilon, that I'll have to find that epsilon only depends on that function, okay, not on x, okay. So now look, he is defining on, and I'm taking even just. Look, since fnx going to this for each means fnx pointwise, it is fx increasing so that fx is greater than equal to fnx. That's why I'm not taking mod here. This is a positive number. So this is actually 0 less than equal to this. He's taking that. So this is same as this. N, you have picked up any n and keeping it fixed. Okay. Now look, this actually means same thing. Sorry. So that actually it means you could write straight here. Actually, I should have one more bracket actually. So this actually even actually means this, but both fn are continuous, and it's a neighborhood of 0, open set. It's an open set in R. Okay, and both f and fn continuous. So f minus n continuous. So global definition of continuous, the continuous image, inverse image of an open set is open. So un is open in X. Now look, where I have used pointwise things. This is fine. This is I have only used this thing. I have not used pointwise convergence. I have used only fn continuous, f is continuous. Now look, you should check because since fn converges to f pointwise implies x equal to this. That means each x if you take, then fnx converges to fx. Then for even you have picked up epsilon, right now you are keeping it fixed. Then given that epsilon, I will get n naught such that for all n greater than equal to n naught. Particularly it is true for n naught. That means it will belong to un naught. This thing. So this you are getting that pointwise implies. Here you are using pointwise. Okay. But each condition is using. But I am saying now compactness. Since X is compact, it will have a finite subcover. Okay, so that it will be look like this: UK1, UKN. Okay, right? It will cover X. That is TKM. Okay. Now look, you can check that because of the definition of UN, and Fn is this. Okay, increasing. Then what will happen? Then you can check this will have this. It's because of this. You can just take the user definition of a UN and Fn that increasing. You'll get this. So that here finitely many you have this. If you take n equal to n not equal to max of this, then actually each of them will be contained max of this, so that uki will be contained in u n naught. So that means x will be equal to n naught. That precisely will say that it is uniformly convergent. Okay, that precisely will say, because they for all and since un naught is this, whenever n greater than equal to n naught, that means particularly you will get x equal to un for all n greater than equal to n naught. That exactly said what? That fx minus fnx less than epsilon x equal to un, and un is this for all n greater than equal to n naught and x equal to n, and for all x belongs to x. That precisely means uniform convergence. Okay, so you are getting given epsilon, this n naught you are getting, that only depends on epsilon, not on x, because for all x. So uniform convergence. So this is the proof. But now what I want to tell you that after telling you that I will take a break, then I will come back. Look here. Look, I was getting this cover. So actually I was getting countable open cover. And I wanted a finite subcover. This book was on the analysis, real analysis. That's why they didn't talk about countably compact. But if I had countably compact, X is countably compact. Still, I will have this. So then I will have this finite subcover. That means in this theorem, Dini's theorem, I will tell more actually. Let me see. If I have an e-copy of my paper, I will give you that. That Dini's theorem, Stone-Weierstrass theorem. Finite subcover. So that in Dini's theorem, you need right now X to be, you need X to be countably compact. You don't need to be compact. It's a weaker condition. In fact, still it can be weakened. Let me tell you that countably compact. So Dini's theorem holds for countably compact. There is a concept pseudo compact. What is that? You should know the meaning of pseudo. It is in disguise. Pseudo compact. Usually we take Tychonoff space because of the non-trivial continuous functions. But in general, I can define a topological space x tau. But usually the authors take it to be Tychonoff space because continuous functions is coming. It's called pseudo compact if every real valued continuous function on x tau is bounded in basically R. That is, for each f belongs to Cx, fx is bounded in R. Okay, this is called pseudo compact. Now, what I want to show that countably compact implies the proof is easy. But I think I have taught. Again, I'm telling you pseudo compact. Okay, and how to prove that? Now look, if you have a countably compact space X star, okay, continuous image of a countable compact space is countably compact. Okay, and continuous image of a pseudo compact space is pseudo compact. So X star, if you suppose it is countably compact. I'm saying if you have this, each real valued continuous functions is bounded. If you have this, implies f is bounded. Okay. How to prove that? Fine. Now look, here what you do, fx is a subset of R. Okay. Now R I can write this. Okay. So that fx equal to this. Okay. Right. Now x is f inverse R. It need not be the whole thing, but it's not a problem. F inverse of this. So that means that you get this. Hmm? Look, since f is continuous, each of them is open in X. But this is countable family covering X, and I have assumed countably compact. I have assumed countably compact. So there exists a finite subcover. There exists a finite subcover. Like this. Of X. That means what you are getting? You are getting X equal to union मैंने क्या लिखा है इधर माइनस एन के यस here again the previous argument you see that if I take m equal to max nk समझ गया so this will be actually bigger than that. That means what you are getting? You are getting actually this is the whole thing. That means precisely f is bounded. That means every countably compact space is pseudo compact. But there is not much difference between countably compact pseudo compact. Let me tell you that. That so countably compact implies pseudo-compact. But there are pseudo-compact spaces which are not countably compact. But the good thing that in a normal space, if your space is normal, in particular T4, for a normal space, these two are same. In Wheeler, you look at section 17, he has the problem. Let me tell you, I think I have told you that to look at the problem. Sometimes it's enough to look at the problem. Let cut it off. Yes. So let me tell you that. Yes. If you're interested, you can try to look at the proofs on that. This is Willard. The pseudo-compact T4 space is countably compact. He's taking T4 because he's defining on X a space is called, so it is T4 space. I think you need that. Okay. Normal plus Hausdorff. Okay, so that we learned page 126, problem number 17J. You should look at these problems. Click the statements. Okay. Right. The pseudo-compact T4 space. If you can work that on T4 space, they are equal. And why T1 is required, I'm not very sure about it. I think it normally it should work. Okay. So that look that. So that countably compact, pseudo-compact is this. What I want to tell you, the Diniz theorem actually equivalent to means. Let me explain. That I will, if I have the e-copy of my paper, I will upload them. Pseudo compactness. Look, if it is pseudo compact, Diniz theorem holds. It means if Diniz theorem holds on it. Look, if it is X tau is pseudo compact, then Diniz theorem holds for any. On the other hand, what do we mean the Diniz theorem? Suppose you have this condition that whenever this is a monotone function and converging to this pointwise, it implies for any monotone function converging pointwise implies Fn converges to F uniformly. Suppose you have it. Suppose for any monotone function, I don't know any function, for monotone function, converging to F pointwise implies, suppose this is your hypothesis, then it can be proved that it has to be pseudo-compact. So that pseudo-compactness can be characterized in terms of the Diniz theorem. Why I want to tell you that? Because I will teach you Stone-Weierstrass theorem approximation theorem. Stone-Weierstrass theorem actually characterizes compactness of a space. So that is the difference. Now here, so let me tell you that in the metric space, what will happen then? Metric space, we have seen that countably compact, that we know that, if and only metric space. But metric space is a T4 space. If and only if it is compact, sorry. But metric space is a T4 space. But here is the proof is not easy, but you can have a different proof on the just for the metric space. So that in Ali Francis Barkinshaw, look at this thing, page 56, number 12, is saying, look, this is same as this bounded. Look what this problem is saying. This problem is saying show that a metric space is compact. Metric space is compact if and only if every real valued continuous function attains a minimum value. That in particular it is bounded below. Once it is compact, then obviously the bounds will be obtained. Attains a minimum value. Now look, this thing means the function is bounded, because if f attains minimum value, then minus f, look, is another continuous function. So this attains a minimum value. This attains the minimum value implies f attains the maximum value. So that means f is bounded. F attains both maximum and minimum. So f is bounded. So this is the thing. You think of that, whether you can prove it, that Xt is compact. Here essentially this problem says the metric space is compact if and only if it is pseudo compact. Okay. So that much I have told you. I will come back now. That I want to teach you something more. Well, here come this thing. The, suppose you have a nonlinear space now. Nonlinear space is what I'm writing. Well, look, it's like this is generalization of this basically, this concept. Look, I taught you last semester. Again, I'm mentioning. Here, usually, when you say bounded, a set is bounded. If you say A is bounded, if there exists M greater than 0 such that okay, so but this means actually which means dx0. But in the metric space, don't do that. We have the concept of boundedness. There we take the diameter basically. If you have a subset of X, take a non-empty set. Okay, and A is bounded if and only diameter of A is finite. And I told you that I think I given a result to you to prove exercise. Here the difference is that in R we are taking a reference point 0. Okay, if you have this and you can show that this definition also follows because if you have this, that means what I have given you last semester. Okay, last semester I have given you this result. We call that let XD be a metric space. Actually, I want to go to Ascoli-Arjula theorem, more general version. So that's why I'm talking about this metric space at x naught belongs to x. The following are equivalent. A. Diameter of A is finite. It means that is A is bounded in the metric space xt. And B, you have taken this point, any point, that sup of d x naught x belongs to A is finite. Here I am calculating the sup with respect to a point. It's called the reference point. And here I am doing in between them. Okay, these are so we do it in R. We take actually x not equal to 0. Okay, so that in case of a nonlinear space, look, the metric is coming from this thing, similar to this. So here I can also take, look, this is a metric space. I have this concept of the metric diameter. At the same time, I can take this x equal to 0 if I take, and that is called norm of x. So that means in a nonlinear space, I have this concept is equivalent to the concept of the boundedness in a metric space. So the definition, let be a nonlinear space then you say that A is called bounded or non-bounded. if there exists m greater than 0 such that this for all x belongs to A. So because of this result, non-bounded will be same as the bounded in the corresponding metric space. Okay, why I am talking about this? So non-bounded, so in a nonlinear space we have the concept of boundedness, similar to the metric space, which is equivalent. Now look, if you have this px, here x is just a non-empty set, it's a set only. And with this, we are taking this metric. Okay, right? We are taking this metric. That means norm. Norm is here the function. I already told you the norm is defined here. Sup of fx because bounded function. Okay. Now look, in Ascali-Argela theorem, there is two things come. They call it so-called uniformly bounded. Now look, here I'm taking bounded. So if f belongs to bx, there exists m. This m will depend on f. So such that since this is a bounded function, but this will depend on this. That means if you change f, in general this value will change. This value will change. On the other hand, if you suppose I have this, and suppose S is bounded in this space. Students, they always confuse between this bounded thing and that. Okay, but there is no reason for that confusion. That's why I'm spending time. Bounded in this space. That means what I explained, it means there exists m greater than 0 such that this is the norm. Look, to have this is this. That means in particular I am getting this. Look what I am getting. For all x belongs to x. Because soup is less than equal to m. So obviously this. So I am getting this for all x. So for all x matlab like uniform convergence, it came for all x. So you are having this. So if you have a bounded here in this nonlinear space, you are getting this. That means look what is happening. Right? Now look, here it is a bounded function, no problem. So I am getting this, but here look. So if you change the function, it will likely change. But when you have a non-bounded subset here, look, same bound is working. That means this MF is independent of F. Same M is working. In this case, we say that means, of course, they are for bounded functions. But here we are having so-called uniform bound. Uniform bound. That means this bounded in the special case of function, we can say that this collection F is uniformly bounded. That means this. That means we say F F belongs to S is uniformly bounded. That is one single bound is working. That means also it is happens if and only S is bounded in this nonlinear space. I have taken a subset of this non-empty subset. So S is uniformly bounded is nothing but is bounded in this nonlinear space, the corresponding metric space. So uniformly bounded, you should know that. Here, when I'm taking bounded function, for each function I have a bound. But if you have a collection of functions, if one single bound works for them, like the uniform convergence, I can use the term uniform bound. So uniformly bounded. So Ascoli-Bargella theorem, that it comes uniformly bounded. So this is uniformly bounded. Now there is another concept that I will tell you explain from my book, that Ascoli-Argentino, how much it can be generalized. So that this is uniformly bounded, means it is. And when we call it pointwise bounded, S is called like pointwise convergence, uniform convergence, similar concept. And S is called pointwise bounded. S is this. Called if for each x there exists a max, it will depend on x, such that here look, for each x, that means if you change x, it will change, but it is always for this, for all f. Okay, so this is called pointwise bounded. This is called pointwise bounded. That means what I am doing it. That means fx f belongs to S. This set, this is a subset of R, is bounded in R for each x belongs to. That's why I've changed this. This is definition. This is called pointwise bounded if for each x belongs to this. So you can easily check if it is uniformly bounded, it will be pointwise bounded. So that if you have this, you can easily check. Like uniform convergence implies pointwise convergence. So if you have this, then the result, simple thing, proposition, you can prove that. If S is uniformly bounded, then S is pointwise bounded. समझ गया? But S is uniformly bounded, don't forget, it implies boundedness in this nonlinear space, that is the corresponding metric space. I'm trying to explain. Of course, you should read the proof, you should understand the proof, but more than that, first of all, you should understand the statement of the theorem, why it is important, why people are crazy about Ascoli-Argentino theorem. Okay, more than the theoreticians, the applied mathematicians use it in them. Okay, so that if S is uniformly bounded, then S is pointwise bounded. But you should look at what the pointwise bounded subset of Bx need not be uniformly bounded. Exercise, find a counter example. That means example basically. When you are dealing with functions, two ideas come, uniformly bounded, pointwise bounded. Now, like Dini's theorem, That is another theoretical, philosophical motivation. That in Thiny's theorem, we are thinking that when pointwise convergence will imply uniform convergence. Similarly, Ascoli-Archila theorem, we can why Ascoli-Archila theorem particularly important. Essentially, Ascoli-Archila theorem, people say, of course, characterization of compact subsets of that Cx. But the point is that more than that, actually related question is that when pointwise bounded will imply uniformly bounded. That means if you have this, particularly if you take CBX, continuous functions, if you have this, S is pointwise when this uniform boundedness concept you should understand. If you don't understand, you will have problem next semester in understanding principle of uniform boundedness. S is uniformly bounded. Philosophical idea of principle of uniform boundedness is similar in the function analysis. Principle of uniform boundedness. Philosophically, the idea is similar. PUV. The next semester you'll be doing that. So this is the question. This is actually related to Ascoli-Arjula theorem. So next time I will talk about this. Actually, I will give you the proof of Ascoli-Arjula theorem, the Jan version from my book, and then I will also talk about the. I may not give each and every detail of the proof what Aliprantis Barkinsa has given for this. So next time, tomorrow I'll talk about Ascoli-Arjula theorem, this one. So, but before that coming, make sure that you understand pointwise bounded and uniformly bounded. These two concepts. Understand. I think some of you onboarded, so you'll miss your lunch in the hostel. I think so. I leave it here. I'll meet you tomorrow. Okay. See you. Bye.